Hello, hello. My name is Maksim Jenihhin. I'm an associate professor at TalTech, Estonia, leading a research group on trustworthy and efficient computing hardware. And today, here with me, Davide Bertozzi from University of Manchester in the United Kingdom.
Thanks for having me here.
Yeah, and also Frank Gurkaynak from ETH Zurich in Switzerland.
Yeah, thank you for having us here.
Okay, so the focus of our discussion today will be reliable and efficient AI chip design. So we know that over the last few years, artificial intelligence has passed through different areas of our life, including healthcare, transportation, security. And actually, this has introduced very interesting new requirements to the software and hardware components of these applications. And at the same time, these new requirements, they provide some special opportunities for technology-oriented universities such as TalTech and technology dominating countries such as Estonia. And now we would like to discuss this topic, what kind of opportunities are brought by this trend. So first of all, I think that it's interesting to discuss the recent transformation of AI by its fusion with edge computing. So artificial intelligence is increasingly brought to the source of data, to the devices at the edge of network, and it establishes a new concept of HI. So let's first understand what are the key advantages and challenges of this trend. So I don't know, Davide.
Yes, I mean, since the advent of the first silicon computers came the ambition to design machines that can think, so to say. And fundamentally, this was fueled by the transistor integration levels over the last decades and to the advent of GPU computing. Fundamentally, today we have finally forms of embedded artificial intelligence which draw inspiration from the way that the brain processes and organizes information. It's all about, processing through a densely interconnected network of computational elements, which are the neurons. And that's what artificial neural networks try to reproduce, right, by taking a vague inspiration from the brain. And fundamentally, today we have the possibility to exploit this in a huge amount of applications with significant impact, ranging from machine vision to natural language processing. And today we are really nearing or outperforming humans in complex benchmarking data sets, games, and even medical applications. So the latest frontier of this consists of bringing this intelligence not only in the cloud, but outside cloud computing sources to the environments of everyday life. And this is extremely challenging because fundamentally we need to provide intelligence to devices that are constrained in terms of resources, in terms of power consumption, because many of these devices are also battery operated. So this is actually a challenge in itself. And from this viewpoint, the consideration, very interesting consideration, is that although this is happening to some extent, because today we are working on artificial neural network accelerators that are more and more power efficient, we call this tiny machine learning, as a matter of fact, we are still far away from the efficiency of biological brains because, for instance, an honeybee brain consumes roughly 10 microwatt to perform real-time navigation, pattern recognition, and constant adaptation to the environment. In contrast, our ANN accelerators currently burden on the order of milliwatts just for basic image classification. Then there can be, more efficient devices, but this is a rough estimate. Therefore, being able to provide intelligent edge devices within these tight power budgets is still an open and daunting challenge. And for this, we need to improve our capability to design efficient AI chips.
Okay, but then what is the key difference between AI chips and non-AI chips?
Well, there is a profound difference, which is given by, I would call it an elephant in the room, which is the vast computational complexity of these algorithms. Because fundamentally, let me provide you an example. So let's consider the Asian game called Go, which is in our community well-known proxy for application complexity. And here we can see an interesting trend. The first machine that was able to defeat a human professional player consumed roughly 40 kilowatts. Today we have new algorithms that can outperform any human player and consume roughly 1 kilowatt. So there has been an improvement. However, we are still far away, actually 2 orders of magnitude far away from the 20-watt power budget of the human brain. And this holds at all scales and levels of complexity. So for all the cognitive tasks that we can think of, the power and area efficiency of current AI systems lag behind biological ones. So the question really now is, how can we reclaim the power efficiency gap? This is the daunting challenge for AI chips that makes them so special.
Okay. So let me also understand the following. We talk about chips and tailored chips design, right? And maybe, Frank, you can help me to understand this. So consider a process of chip design. Does it really mean that always a very large team would need to be able to design each time new complex hardware architectures, and also to have these super expensive licenses for the software which is used to design this chip, so-called electronic design automation software? So from your experience, is it really so difficult?
The driving force behind this is what we call Moore's law. So essentially every 2 years, 18 months, we were able to double the complexity of things we were designing. So this roughly translated means 100x improvement over 10 years. When you think about it, something that you've designed or you were working 20 years ago is now 10,000 times simpler. This, on one hand, allows you to make very, very complex big systems, like what you see today in NVIDIA, those big GPUs. On the other hand, it also translates that something that was, let's say, 10 years ago only possible to design with a very, very large team can now be designed with a more modest team, because we increase the productivity to be able to design enormous chips. But those productivity increases also helped us design smaller chips or chips with more, let's say, modest parameters to be designed within reasonable effort. So, for example, in our institute, we have a student program where students within 14 weeks can take an idea, and quite advanced idea actually, and realize a chip within 14 weeks, 16 weeks time frame from start to finish. And these chips are, let's say, comparable to what people would have been able to, or larger corporations would have been able to do 10, 20 years ago, I mean, roughly speaking. This doesn't mean that these chips are not doing something very interesting. They are actually quite, there's so much room for innovation. And as Davide was saying, we are trying to make things near. We are not trying to, I mean, there is the effort of putting things near where the signals are. So that's the edge AI. And in those places, we cannot afford to have big GPUs, big computers. We are trying to come as near as possible to the signal source and make a reason about the signal, make decisions about it at the source, so that our communication goes on. And there is so much variation in it. This could be very simple signals like water pollution levels. It could be more complex, like monitoring traffic or things like that. But the computational demands are actually, you can meet them with the simpler designs that smaller teams of maybe 5, 10 people can manage within a reasonable amount of time. The same also works for the tooling. For the very, very large designs, we needed state-of-the-art tools and then very complex EDA software that was provided by a number of providers. But recently we have seen that open source EDA tools are also able to step up, and slowly they are catching up on being able to help researchers like us to to design chips that are meaningful for a research and also economical context for a wide variety of applications. And the primary of them would be obviously HAI.
Right. But then similar to what we have for EDA tools, electronic design automation tools, software, right? Can we do something on the hardware side to help us not to develop these architectures from scratch each time, but to share the knowledge, to share the results of the previous projects?
Yeah, that's an excellent point. You know, maybe 20 years ago, 15 years ago, making one processor was the entire chip. But right now, there is so much what we call commodity pieces that make up a large complex chip. So frequently a modern system on chip, an HII processor, would have a couple of processors, many interfaces, all of which can be designed separately, made available, and shared between people. Now, just like open source software movement, there's been a recent movement in the last 10 years about open source hardware, where we started sharing these blocks, these smaller blocks, what we call commodity hardware, between research groups and even companies. And so this is getting more and more interesting because it allows you to concentrate on the secret sauce of your HAI processor and not on the parts that will be common between many, many other designs.
Right. So actually, I need to mention that this week we have just kicked off a new European project called TAICHIP. And the title of this project is Boosting TalTech Capacity for Reliable and Efficient AI Chip Design. It's a twinning project, and here University of Manchester, represented by Davide, and ETH Zurich, represented by Frank, also along with University École Centrale Lyon in France, and Research Center IHP Microelectronics in Germany. So these four academic partners, they participate as advanced partners. And we are starting this project. You are participants there. So maybe you could summarize, you could outline what can TalTech learn from your institutions, and how can it be useful for Estonian people and businesses?
Well, first of all, I would like to say that University of Manchester is proud of contributing to this project and to partner with TalTech to bring its research and innovation capacity to the next step. And by the way, social impact is in the DNA of our university, so our participation to this kind of European project is pretty straightforward. And we are the only UK university to have social responsibility as a core goal. More into the details with this project, I think that the mission of our university engages in another global partnership to improve the sustainability of communities worldwide. So I'm pretty proud to be part of this project. What, in my opinion, we can share with TalTech are some of the distinctive features of our academic life. First of all, to continuously work toward an inclusive institution at all levels. To help the brightest research ideas to find their way to the market in terms of either industrial licensing or creation of spin-out companies. And this is inspired by what's going on in Manchester. We have the Manchester ID Initiative, which is a £1 billion innovation district which has been developed in the heart of Manchester. And this is a pretty original, interesting experiment for other cities as well. Moreover, we put a strong emphasis on the growth and lifelong development of researchers so that they can fully deliver their potential, already starting from the stage of a PhD. And we can share the best practices in research management and administration from a large-scale institution, such the one that we are, with 44,000 students and 13,000 employees. Then I would also like to mention the fact that what we can share is the expertise in bringing in taking research ideas from everyday's work in research into high impact projects. We have the example of the Spinnaker projects. In fact, in Manchester, the first large-scale neuromorphic supercomputer has been designed, is actually currently working. It is the outcome of 20 years in conception and 10 years in implementation, and has attracted 15 million pounds in funding. And this is a very interesting initiative that we can share with you, and that we can actually communicate the way we went through the entire path. Last but not least, we can you can be inspired by our top-class blended learning and teaching methods, where the contribution of pedagogists is fundamental to shape the way we deliver our teaching. Last but not least, we can share our research vision. Our research vision is that in order to deliver more efficient AI chips, we should turn more and more to biological brains and be inspired by the way they compute, they represent information, and they communicate.
Sounds exciting. So, Frank, what about ETH?
Yeah, well, our research group, so Digital Circuits and Systems Group of ETH Zurich, we are specialized in designing energy-efficient computing architectures. Essentially, we design integrated circuits. We are relatively good at it. And we've been active for more than 10 years now in open source hardware. And being able to collaborate with TalTech, sharing with them our design experiences and helping them to gain more experience in designing their own ICs is for us very exciting. We don't see this as a one-way transfer because TalTech has been active in a number of research questions, and we find it exciting to be able to also combine their research ideas with our, let's say, practical IC design, open source hardware related activities. And we hope in 3 years we'll have a lot of fun together and, generate interesting results.
So, you remember when I mentioned the title of the TAICHIP project, right? Boosting TalTech capacity in reliable and efficient chip design. So these two terms, reliable and efficient, and when we talk about efficiency, it's usually energy efficiency which is in the game. So let's elaborate a little bit on this topic. So because I think that it's also very interesting. So now we are in the era of extremely small nanoscale transistors in the chip, right? And they count billions. And at the same time, when we talk about AI applications, then the reliability of physical chips, they establish this the most fundamental and first level of reliability of any trustworthy AI application. So what are the main threats to the reliability of chips and AI chips in particular today?
AI systems, HAI systems, and normal AI systems are taking over more and more important functions of the world. So it's not only the technical challenges that come with it, but its application fields are taking over functions that you can no longer accept failures. So from an application point of view, reliability is becoming more important because of where you are putting, let's say, if this mouse malfunctions that Davide has here, and it's just jittering a little bit, it's not the same as some AI functionality which is making maybe in your car some decisions or something like that. So that's the first thing. So there's increased requirements on the reliability from a functional point of view. The other thing, as you mentioned, is you are pushing the limits of technology. You're trying to put more and more things together. You're developing more complex systems that have many more problems that can come up within the same volume, within the same area. That also makes a problem that you could maybe previously, I wouldn't say ignore, but can maybe tolerate a bit more, ever less tolerant. So you have to be even more. So everybody is aware of that, but not enough is being done at the moment. So research in reliable systems is an area where I believe more and more work will have to be done, and this is also one of the interesting reasons to be able to collaborate with a group that has been working on this for much longer than we were.
Mm-hmm.
Yeah, I fully agree. And I would like to stress the importance of emerging autonomous systems in this respect, because fundamentally they are becoming an integral part of many Internet of Things and cyber-physical system applications, such as automated driving, robotics, avionics, industrial automation, and smart systems. And this has huge implications on human safety. And from a technical viewpoint, this poses unique challenges for the design verification, as well as this is a great addition for us, as well as runtime monitoring of these autonomous systems. Because, you know, in addition to the sources of unreliability that Frank was mentioning, I would add the fact that these edge devices will operate more and more in open and evolving environments, which are not necessarily defined at design time. So while it's relatively simple to test these devices against design time conditions, it's not trivial at all to test them against runtime conditions, which are highly unpredictable at design time. And this is a unique challenge for this kind of systems. Last but not the least, we have to mention that we are manufacturing devices with scaled dimensions, and this is an inherent source of reliability, because we have to expect these devices from time to time to fail. And we need to cope with that, of course. And from this viewpoint, I think that the TAICHIP project had a great intuition. The intuition of the TAICHIP project is to monitor these devices at a runtime as the key to preserve their reliability. And for this, we can use intelligence to monitor intelligence. In practice, the intuition of this project is that AI can be used to monitor the activity of a chip and to understand whether there has been the onset of an hardware fault or not.
Great. Yes, I think that that's very important. So some chips can be designed by teams in California, right, where snow is not so often, and then they are used to here in Estonia, and then the training sets for the vision or some other constraints can become quite different from the place where the chips were designed. But there is also this second aspect, which is very relevant and very critical for the AI and in particular HI chips, right? So energy becomes the most expensive resource in our world. And the energy efficiency of chips can even become an enabler for some particular AI applications, right? So what is important in this aspect? How it can be addressed in HI chips?
Well, in this respect, it is very important to learn from biological neuroprocessing systems and from the way they can attain energy efficiency. In fact, if we look at how current tiny machine learning devices are designed, we can see that they are unmistakably trending toward the key properties of biological systems. In fact, we tend to co-design processing with memory. We tend to go for event-driven processing, and we tend to go for low-precision computation. We are actually going in the direction of the operating principles and information representation of the brain, although this is still a long way off. So, in my opinion, even without going for disruptive models of computation, such as spiky neural networks and other more exotic technologies, current AI chips could largely benefit from increased levels of dynamic adaptivity. Let's think about how it works for human beings. So when I come across my mother, I do not pay too much attention to the face expression, to her dressing, these kind of things, because I know she's my mother. So my interest goes in other things. Instead, when I come across somebody who I don't know, I pay attention to such details in order to understand what are the intentions of this person. Which means that if you take inspiration from this, we could devote as much computational power as required by the input that I'm processing at a certain point in time. So, for instance, let's make the example of object classification. If I want to classify object with a homogeneous background, it doesn't take a lot in terms of computational horsepower. While if the object emits a wide variety of background objects, then it takes more computational effort. Therefore, we could make the power consumption of AI chips highly adaptive to what I'm doing at a certain point in time. And from this viewpoint, we're again taking inspiration from the continuous adaptivity of biological brains to the environment.
Okay.
Yeah, from an IC design perspective, as you say, the energy is a very precious resource. So if you have a battery-operated device, there is some power source connected to it, and it has limited electrons to do something. And our job is to eliminate waste. We need to make sure that each and every electron there does something useful for us, then we have achieved perfection. I mean, joking aside, this has many forms like dynamic load adaptations, clever algorithms, quantization, adaptive systems, and many more. Since we have so many knobs we can play on, there is also a large number of advancements that we can expect from this, and we are excited to explore some of these as part of the TAICHIP project.
So basically, we are talking about application-tailored chip designs, right? And runtime adaptation to the context.
Absolutely, yes. Because, you know, the moment you have something that is generic, something that can cook food and detect people on the street, it has to have a lot of resources that can be used for doing anything. But the moment the application becomes clearer, if you're just doing face detection, for example, you can throw away the things that you will not be needing for face detection and have more efficient, more tailored systems. Now, the difficulty is making one generic system you can use for many, many applications. Once you need to tailor things for specific applications, this means that there needs to be people that can design these and implement these. And this is exactly the part that we are trying to make easier, make these more accessible, so that the amount of options you have for solving the problems also include maybe custom IC design for HAI applications.
Right, so this problem of more different chips needed in the world, right? I think this is also addressed by the European Chips Act initiative. So that was launched a year ago. And maybe you could summarize, what does it give to the community? What is it all about?
Davide is looking at me. So essentially, what has been realized very publicly is that Europe has been a bit late in investing into making its own integrated circuit. So we rely in mainland Europe, let's say, more and more on foreign countries and companies to deliver the integrated circuits that are needed for everything, from voting machines to computers to simple entertainment devices, cameras, microphones, you name it. And we need to close the gap. And this has been publicly recognized. And the European Commission has launched this initiative, which has many different pillars, among which there is also a lot of support. And we believe this is very important if we want to keep, as people living in Europe, if we want to keep up with the trends, we need to educate more people, we need to have more experience in this, and also allow companies within these countries to innovate in these fields. Otherwise, we will be dependent on other geographies.
To this, I would like to add that the European Chips Act is triggering a healthy competition in the UK because, of course, of its particular position outside of the European Union. But the European Chips Act has led the UK to boost its production of semiconductors in order to face the competition from the world giants. And this is taking interesting effects because the UK is smaller than the other competitors. Therefore, it really wants to get more value from the invested money. And from this viewpoint, it's focusing a lot on funding startups, which is very good news for an economic growth fostered by widespread innovation. My wish, of course, for the future is that we will see a strong collaboration between the UK and the European Union, since the European Union has a highly skilled base of engineers that has huge synergies with the UK ecosystem.
Mm-hmm. So actually this European Chips Act and also this number of other initiatives which are launched in other countries like United States, South Korea, India and China and Japan, they are not only about the financial aspect, right? Because you cannot solve everything just by the money. It's also about the workforce, the qualified engineers. So in this context, right, how TalTech and Estonia can contribute to the CHIPS Act to help Europe to actually reach the level where this domestic chip production would be increased.
Yeah, I mean, the problems that you can solve by throwing money at are the best problems in the world, right? You know, you just throw money at it and it's solved. But as you say, it's not only money, you need people. But actually, as a resource, if you think about it, Estonia does not at the moment have much involvement in integrated circuits. But it is there, actually. You know, there are people that are capable, there are good schools, so there's no reason why Estonia cannot produce a significant number of engineers that have experience in this field, found companies, startups that are active in this field. So the fact that there are not at the moment doesn't mean that there is anything, how shall I say, inherently missing here. It's just that it needs to be unearthed. It needs to be brought to the surface. And we are hoping that TAICHIP could give a spark in this direction, have the starts, and maybe in 20 years, Estonia would be one of the leading companies when you're talking about HAI chips, for example. Why not? I mean, it has everything it needs to do it.
And I think that at this particular time, it's very critical that our university can also acquire some experience in education from ETH Zurich, where you have very strong lectures, and also from University of Manchester and other advanced partners.
No, these are absolutely secret. We will not share it. Jokes aside, no. We believe on open science. We believe on open source hardware, education, and things, and we are trying to move more and more for lectures that are openly available between different people, because we are not doing this out of a altruistic, idealistic issue. We realize we need more input for our lectures so that they can become better, and we need a larger community to help foster them. Alone, we are not. We reached a level where we can go alone. But now, to make the next step, we need the help of everybody. So the open communications help us grow both the infrastructure, tools, lectures, and everything. And this is part of what is needed to be competitive again in this field.
Great. So thank you, Frank. Thank you, Davide, for the inspiring discussion. And I'm really looking forward to our collaboration in the TAICHIP project.
Thank you very much.
Thank you.